Alright, time for another draftphysics.com, debatephysics.com also, trying to find somebody capable of, responding in kind, that is, with more than just ragged comments, and such. So anyway, I found this guy called Blue Moonshine, and he made a few videos responding to some science crank of some kind, and I was just hoping that maybe I can get him to do the same for me. So the first thing I'm going to say is basically, watch the last video where I used the two examples of good reasoning why kinetic energy as an idea, 1/2 mv squared, the theorem, doesn't work, that it's not intelligent to believe in it. It's making a mistake to think it's viable, because the experiments kind of just demonstrate it, the ones that have been done, the very few. So anyway, and he's obviously, this guy is a defender of that because he has it written right on his t-shirt here, F equals m, and then the derivative crap of dv over dt. So obviously a believer, okay, in the magical increase in your energy for free. So I'll use two examples in this video. One of them is this, okay, where a guy's demonstrating the ballistic pendulum, selling the product, the little toy. And he basically says that it conserves kinetic energy and blah blah blah, and it doesn't. And so I just was going to use that as an example of how they just talk right past the absolute facts and talk, absolute shit. Anyway, then so the other guy, okay, who's arguing with this John Mandelblar or whatever that is, who, and they're using the example of, well, it's hard to explain the example actually. So we'll find it somewhere, I guess, and make the point that, basically spinning an object, and then you make the string shorter, as you're spinning it. You make the string shorter, and it looks like it spins faster, but it doesn't. And what they're doing is counting its radians, how many, how fast it rotates, and how fast it rotates, that is, how many times it makes a circle, doesn't have anything to do with it. Obviously, the idea is it's going to conserve its momentum, so it's going to be going the same speed. It's just going the same speed in a smaller circle. And so it does conserve momentum, and it really doesn't have anything to do with kinetic energy, but whatever. And then this other experiment where he did, this is the one, okay, here, the angular momentum is the one about the spinning thing. And then he's going to demonstrate the kinetic energy theory by just shooting an object, rolling an object with a fan on it, which is exactly the same as letting the energy dissipate out of something. Obviously, as the object goes faster and faster, it gets less and less friction, so it's exactly the opposite of just rolling something, pushing it, and watching it slowly lose all of its energy. So essentially, it's the same mechanical system. So obviously, he's saying because it's going more distance, okay, as it goes faster, that somehow it has more energy than just the, like, twice the velocity ends up being. You're able to move more than twice the distance because of the fact that the friction is getting less and less the faster you go. So it's exactly what's illustrated in the last video I made, in the sense that you have to believe that somehow friction is constant when it isn't. It's constantly changing as your velocity changes. So I'll illustrate that point. And then he says something that's just wrong. Alright, so the wrong thing said is in this video, so we'll play a little bit of this. So here's the example of the guy he's arguing with. Unfortunately, I didn't see that coming. Alright, so this is the guy. He's twirling it and then pulling the string through his fingers to make it a smaller and smaller arc, and drawing some conclusion about how in radians, okay, it's supposed to go this preposterously high, and obviously it would, okay. As the circle gets smaller and the velocity stays the same, obviously it's going to appear like it's, going many, many revolutions, but it's going many revolutions at the same velocity because it's a much smaller circle. Duh.
No, it most certainly was not 12,000 RPM. But was it 600 RPM? What's it doing right here? Seems to me the yo-yo has come to a complete stop.
Alright, so that's sort of irrelevant. The question is if you did this experiment in a better way, what kind of results could you expect? So they have here a video of somebody doing it better. Alright, so I'll go to that. And here, Arso. So this is somebody else's video talking about the subject, so I can't really reference any of this stuff, but whatever.
If I misinterpreted the theory, or my experiment flawed in some way?
Good question. I went searching to see if I could find any other videos that we could analyze. I found this one from the University of Minnesota.
Right, and so again, the argument is that you're going to conserve the momentum. You're not changing the masses, so the velocity does in fact stay the same, and you're just having the same velocity in a much tighter circle. And so, again, it's not even complicated, frankly.
And here's one I found from the University of Iowa. Now, neither of these videos provided the numbers themselves, but by analyzing the video, I was able to make some estimates.
Right, and so, all of this is this analyzing crap, and it basically is confirming that it's conservation of momentum, except he's using radians and just making the thing a lot more complicated than it needs to be, frankly. And then somewhere in here, I believe, is where he says the magic part. Okay, so maybe I'll draw this part just to be clear. Alright, so, yeah, you have, let's see, well, I won't worry about the focus yet. So you're just starting with two objects at an arc, okay, from each other, and all you're going to do is reduce that arc by pulling, okay, on a string and changing it to a color that might work. Smaller arc, alright, and, obviously my simple argument is that you're not changing anything. Alright. Oh, I knew the focus wasn't going to work. It's always something. Or it's almost always something. Hiccups now. So obviously the argument is that you're not going to change this velocity. Okay, the velocity stays the same no matter where the arc is, and you're going to conserve the momentum, and the object is going to fly. If I released it from here, or I released it from here, or I released it from here, it doesn't matter where I release it from, it's going the same velocity. I haven't changed anything realistically. And now his argument's going to be, okay, because he used radians instead of using velocity, he's arguing that somehow the kinetic energy does change, that somehow this kinetic energy is different than this kinetic energy, when obviously it's the same mass going the same velocity. And the reason why you're getting a difference is just because you're counting how many times it goes around the circle. Obviously at the same velocity it's going to go around the circle much faster here, many more times. So this might be 100 times around the circle, this might only be 30 times around the circle. So counting radians, counting 30 degrees worth of arc, is a waste of time, because it's not going to give you anything like it doesn't have anything to do with momentum, okay, or kinetic energy. So I don't know how he perverted the concept into a radian mathematics rather than raw velocity mathematics. So anyway, he's going to argue that pulling the string is adding a force, but it's not. Okay, and it's not in exactly the same way that, when you launch something off a cliff, and it travels this way and it travels this way, just as this velocity is not disturbed in any way by gravity pushing the object down constantly, okay, the constant force of gravity will not in any way affect this distance. So it wouldn't matter whether you had gravity or didn't have gravity, it's going to travel the same distance. Okay, so dropping the ball straight down, it will hit exactly at the same time as this one will hit over here, because gravity is completely independent of the velocity because it's tangential to it, it's perpendicular to it. So obviously this force is perpendicular to the motion, you know, the force of pushing down on this string and creating tension, pulling the objects together. All of that is completely perpendicular, therefore it can't affect the rotation at all. So that's just kind of an obvious, simple argument. I really shouldn't have to. He's a physicist. I shouldn't have to explain it to a physicist because they know these rules. They know this rule, that I can apply forces perpendicular to a force and it doesn't change this force. It doesn't add to it and it doesn't subtract from it. So, you know, it's just a bad answer to the question. So let's see if this is where he says that.
When the device is sped up, work is put into the system.
So it's no work is being put into the system you're measuring. So the quantity you're measuring, that is the momentum, the velocity of the object, is not being changed by the addition of the force, just as in this example. Oh, I gotta put the video back up. Yeah, it's a good thing this example did. Alright. Well, you really don't see much in this video.
So it really should come as no surprise that every time we...
I don't know if that's enough volume, so I gotta check the volume. It's probably too much, right? Yeah, probably. I wish I could see both at the same time. That would make things a lot easier here. Maybe I can do this. That doesn't really work. Yeah. So I have to change this. Oh, come on. Change this. Alright. Well, I'll make it bigger. Alright. Let's see. What's the... Oh, yeah. His velocity is way down. Okay. So he said the work. The work doesn't... You know, you're putting work in. So he said here you're putting a force in. He said a lot of things. You're adding a force. You're not, because it's perpendicular to the force you're measuring.
Squeeze the squeezatron, the device gains energy, and the conservation of energy model really is not expected to hold for this case.
So it's not expected for whatever reason. So again, it's just this canard where they claim that this thing is conserved, and then they say, well, it's not conserved arbitrarily. Will decide when, in what cases it's not conserved. And so again, it's just, and again, it's not a matter of measuring radians, it's a matter of measuring velocity. And the fact is the velocity doesn't change. It doesn't change. The momentum doesn't change.
Instead, we expect the conservation of momentum model to hold, and what we've established is...
So again, they're conceding that these two models are not consistent in the sense that you can't conserve both of them in a lot of cases. Now, this is a case where you should be able to. So if he didn't do the calculations by radians and he did by velocity, well, of course, you would conserve it because you're not changing anything. The mass is staying the same and the velocity stays the same. So therefore, you're conserving the kinetic energy. The made-up energy is going to be the same in both cases. The fake, phony mathematical energy will be exactly the same, and the real momentum will be the same. So you will conserve both in this case. So that's the funny part, is because he did the math in radians, and assuming the number of rotations has something to do with momentum, which it doesn't, you know, wrong answer all over the place. So this is hardly, you know, I Can Science That is this guy's channel. He's not sciencing much. So yeah, how did I move from one guy's channel to the other guy's channel? Well, anyway, it doesn't matter. Yeah, this is an argument against the other guy, but whatever.
that it does a fairly good job. I should stress that all of these estimates are rough ones, and so hitting in the ballpark of 10 to 15% is really not that bad. Furthermore, we do expect the numbers to be lower than the predictions in all cases.
Well, we expect that the system does lose energy. So, yes, obviously measurements in units of, over time are going to get slower and slower. So you're going to lose momentum just to the friction and the other nonsense, the air resistance and whatnot. So you have some expectation that you're not going to get perfect measurements.
And so any estimate that is low really shouldn't faze us one bit. We could take this further by getting a device like this into a lab and performing the experiment ourselves. If we did that, we could measure the actual moment of inertia. And
all right, so again, this talk of a moment of inertia and all that, I didn't play this part, so maybe I'll just play this for the fun of it because it's got some cartoon in here. So obviously not going to do the experiment and not going to prove it one way or the other, not
have to rely on these rough estimates. We could also do more rigorous testing to ascertain how much losses there are in the system that have nothing to do with the change of radius.
So any of these systems, obviously they all have friction. All of a sudden, this isn't even something hard to figure out. You can just watch it and say, okay, I twirled it and now it's spinning and now it's going to go start spinning slower and slower. So that's a duh.
If we did that, we should be able to get a very good sense of the actual torques acting on the system, torques such as friction and aerodynamic drag that we have discounted could be measured and subtracted.
So there's no point in calling these things torques or friction or any of this stuff. We should call them exchanges, and that's all they are. You have contact, you have exchange, and that's all. You're leaking your energy into the environment
from the system to get us a better prediction and hopefully better experimental confirmation. I think I've been reasonably thorough and extremely objective in my analysis of these experiments about conservation of angular momentum. There are many...
So again, I would argue that your analysis was garbage because you forgot a basic principle right here. You just threw it away, that if the force is perpendicular to the energy you're measuring, that force will have no effect on the energy you're measuring. And you just ignored that entirely.
More experiments to look at, and we could look deeper into the theory. If anyone finds this all interesting, drop me a note in the comments, and we'll do more videos about conservation.
Yes, we'll see. Yes. So there isn't more videos and all of that stuff. That would be all nice. So I don't know why I somehow mixed these two channels, but whatever. The subject originally was this guy just doing this twirly thing and saying, well, how come it doesn't look like 1300 RPMs? And obviously there's reasons why it doesn't look that way. All right, so let me play the AP Physics one. But this goes more directly to how there is lots of evidence against this theory, right? Okay, so in the previous video I have the example of the fact that you can give something velocity with known forces and that there won't be any need to put in 9 times the energy to get 3 times the velocity. You only have to put in 3 units of energy. And the simple truth that when you are extracting the energy from something by allowing it to roll on a surface with friction, that you can perfectly understand that it's really just about how much time something spends per inch on a surface, and that will decide how much weight there is. And so the weight changes per inch on a surface based on how fast you move across the scale. So it's just that simple an argument. Their physics is assuming that something weighs the same no matter how fast I push it across this scale. Obviously, if I just sit it there, it weighs its full weight. But the faster I can get it to go across the scale, the less and less and less and less it's going to weigh, because it takes time to have weight. It takes time for gravity to give you weight. And obviously, if you're going over a huge amount of surface, in a 1 unit of time, then you're going to have a lot less weight per inch of that surface. I mean, these are really simple principles. I really shouldn't have to keep arguing this. All right, so we'll play this guy. Definitely need more volume, and we'll hope for the best.
Of physics ballistic pendulum, students can investigate conservation of energy and angular motion.
All right, so there's no conservation of energy ever in a ballistic pendulum. So it's just a lie for him to say it like it happens, because it never happens, ever. So it doesn't matter whether it's a bullet or a little blob. It doesn't matter what the velocity is. I will always not collect the kinetic energy. And I will usually, the slower it moves, the more of the momentum, the higher the percentage of the momentum I will collect. But the point is that always the momentum is substantially conserved, and always the kinetic energy is wiped out. And in the case of the bullet, it's 99.94% of the kinetic energy is not collected in the pendulum, in the motion of the pendulum. Okay, fact. And that if it was, if you did collect the kinetic energy, it would mean you made free momentum, because now you would have a lot more momentum than you started with. So those are your two choices in analyzing these experiments. Do you believe you can make free momentum? Or will you concede that kinetic energy isn't viable because you can't make free momentum? If I collected the kinetic energy as linear motion, it's free momentum. The very idea that they say the momentum is inside that pendulum as heat, so I'll make it bigger. They say it's in here. So the pendulum barely moves, okay, in the sense that you have the heavy pendulum collects the lighter ball. It creates a new MV that's the same as whatever the MV of the ball was originally. You're conserving the momentum. And then they say there's a bunch of heat inside the pendulum. Well, if there's a bunch of heat inside the pendulum, it means that's work. That's doing work. So you have to use some kind of energy or force to do that. So they're saying you can make heat without using something's momentum. So you could roll something on a surface, you could heat the surface, and the ball doesn't slow down. That's their argument. So those aren't viable explanations. I shouldn't have to make these videos. Especially a physicist should know they're not viable explanations. You can't propose the creation of free momentum.
You have a freely moving pendulum that catches a ball that is launched from this launcher. There is a sliding scale that will automatically...
It's kind of amazing that, they... Sorry. They have like this set up to do a green screen. They don't bother doing it. And then, and this is... They're selling their product, so you'd think they could find somebody with a tiny bit more charisma, to do the selling.
adjust to whatever the maximum height is, so that you can easily...
It's all a bunch of little rickety crap that we sell for way too much money, like $346, and it's all made out of plastic and crap, and it's just such marvelous things for all you public institutions to buy. So buy a whole bunch of them for your school system, because you're morons and idiots, and you'll buy anything, any piece of crap for way inflated prices. Can I sell you a 1946 computer? Yeah. This is just, who buys this crap?
You record the angle that the projectile reached, and then calculate what the maximum distance was that the object was raised. This is how the apparatus comes straight out of the box. There is a scale along the launcher mechanism, which is...
But it doesn't mean anything. Don't pay any attention, because it's a 24-cent spring in there.
Just there for reference. It is not in centimeters or
doesn't
meters or
mean
inches. It is simply there so that when you pull it back, you have a fixed reference of lines to measure back from.
Yeah, it's very, very fascinating.
It also comes with a small steel projectile and a
Only one? What if I lose it?
probe, so basically when you have the ball in there, you can easily push it back out
Yeah.
and get the ball out easily.
Sorry, it's all very funny.
It
to
also
me.
has a nice little attachment where you
Look
can
at that.
easily
Yes,
connect
a plastic rickety
a
timing
photo
gate.
gate to, so you can measure the velocity of the ball as it is being launched. And also on the end of the launch mechanism there is a hook, so you can attach this to a spring scale and actually directly measure the force in which you're pulling back on the launch mechanism, and you can have the students use this to calculate the velocity of the ball. Now when you first take this out, you might want to do a couple test shots to make sure this didn't shift at all in shipping. You can adjust this left or right, or on the vertical stand adjust it up or down to make sure it catches the ball properly. Then you simply set the lever arm at the...
So they don't do the experiment, which is also funny, because I guess if they do the experiment, then everybody will say, well, why should I bother buying it when you just did the experiment? So I'll just play you doing the experiment, and then I won't have to buy the machine, because what's the point? I mean, does it really matter whether I see this firsthand or whether I see it in a video? I don't think so. I don't think that could matter.
zero angle, pull it back to the first notch, set up the photo gate in interval mode. Now that everything is set up, we're going to do a test fire. Now you have the angle to which the projectile rose, and you just use the probe, pop out the steel ball, and you're ready to go again.
All right, so I missed it. He said it a second time somewhere in there, and I guess I just didn't. I missed it. But he's basically arguing that somehow kinetic energy is conserved in this experiment when it's completely annihilated and there's no sign of it, and it's destroyed, and it's just garbage. All right, so we're back to, this is the work energy one, yeah. So I'll play this little clip of the fan. So this is all I'm saying is he's just doing the
Watch
same
what
thing.
blueberries do to your love handles.
Yeah, that's really.
Smoothie's a good option.
These are
They're
such
probably
tacky
one of the
commercials,
biggest
by the way,
toys in
too.
5 newtons.
Just terrible. They get away with that. All right.
Now that I know the force that the fan applies onto the cart, I'm going to record the position and velocity as functions of time with a motion detector and see whether they are in agreement with the work energy principle or not.
So again, this is really technically just the same thing as starting with a velocity and allowing the surface to consume the energy. In this case, the initial friction is very high. The fan slowly accelerates. As the speed gets higher and higher, the acceleration is easier and easier because the friction is less and less.
The computer is set up to automatically record the data once the cart is within a distance of 1.5 meters from the detector.
So you can see the slow start, and then it rapidly starts gaining acceleration, more and more acceleration per unit of time, because of the very fact that the friction is going down as the velocity goes up. And it's really not that complicated. And so let's see, I think he makes some sort of argument here at the end. Well, I don't think he does, actually. Alright, so that one's not that interesting. And we did this one. Yeah, so I'll have to find out about this guy. I can science that. I should have seen if he has any recent videos. 2 months ago, good. So I can email him too. Anyway. I'll have to see if he has some other, what is inertia? Alright, that might be interesting. Let's play that one. Alright, so sorry, other guy, to have confused this Blue Moon guy with this other guy, but they were talking about the same experiment. And did I show the video of, yeah, I think I did. There wasn't much to it, the clip of the balls at the different ends. Yeah, you didn't show much of that. Alright, so yeah, so we'll go here just for the hell of it and just see what inertia. So again, there's more nonsense about some concept that there's something other than mass and velocity, and there's something called an inertia that changes something, and there's no such thing as whatever inertia is. There's just masses and velocities, and all you can do is conserve the MV, and there's really no other issue involved. Let's see. Let me just see what else he's got. He's got a response to Peter Lane, so, or Leon, or whoever. So I don't know what that is. Globe simulation, so this is more flat earth crap. Professor Dave, oh, that's interesting. So I'll have to go look up and see what he's saying there. So he's debunking flat earthers, which really isn't much of a thing to be doing with your life. And such. Let's see. Anyway, I'll do this on my time. So let's just hear some of the inertia thing.
Finding the right Medicare coverage starts here. With a Clover Health Plan, you...
Hello and welcome back to I Can Science That, where we do honest investigations of everyday science.
Okay, so that would be nice. So if we have some honest investigating of ballistic pendulums and recognizing that stick a thermometer in the thing. If you're going to say there's, 1,900 joules worth of energy in it, heat, then yeah, it'd be nice if you showed us.
Today's everyday science topic is something we're all familiar with, and that is inertia. I'm sure we all know what that...
No, so again, this idea of whatever an inertia is, there's just a mass, and a mass says, well, I will go if you give me energy. If you don't give me energy, I'm not going anywhere. But if you give me energy, I will go somewhere. So there's no such thing as inertia. There's no resistance to motion. There's no obstacle to it. You have to give somebody food for them to eat the food. If you don't give them food, then yes, they starve to death.
Means, or at least we think we have a good intuitive grasp of it. But what I'd like to do today is take us a little deeper into what we know and understand about the origins of inertia, what causes that, and what do we know?
So the argument is that somehow light things are harder to move at higher velocities. So you can't use the same force to move a 2 mass 1 velocity and then move a 1 mass 2 velocity. You can't use the same force to do that. That somehow the momentum won't be conserved. So I have momentum going in, creating a force, and I won't conserve the momentum. When I hit the small object, it won't move. So if I have it on a lever, let me draw that one. Just because that gets to the Steve Moldhorse shit, and just how bad this physics really, it's just so bad that you people are willing to believe anything. Okay, well, it's clean enough. So, the simple argument is you could set up a lever. I mean, I'd like to do it with just a spring to have exactly the same energy in each time, so maybe we'll do that. So you have the same force, okay, that you're applying. You're going to move the lever the same amount. And presumably, in both experiments, you're going to be able to duplicate exactly the same motion in the lever. So the idea is you pull the object back, and you have a 2 mass, and then you have a 1 mass at twice the distance. It's not exactly twice, but you get it. And so this is going to be a 2 mass going 1 velocity, and this will be a 1 mass, and it'll go 2 velocity because the arc is twice as big here, the distance traveled, if the lever moves exactly the same speed. So the idea is these two, you won't be changing the speed of the lever, therefore the lever consumes the same amount of energy out of the system. So the friction, if you want to call it that, or the consumption of the lever, the amount of energy the lever's requiring the spring to push the lever, will be exactly the same in both experiments. So, it should make for a fairly fair contest. Anyway, their argument is that the 1 mass will only go 1.4. Okay, so I'll lose momentum. And then that argument is defeated by the simple argument that if I did create it without a spring, but by actually moving a 1 mass at 2 velocity. So I have a 1 mass at 2 velocity. And I put that into the lever on this side, that somehow it will create a 2 mass at 1 velocity, that I'll make free momentum. So again, this is, all of these experiments, if taken to what they claim, it's free MV. It's free. They're free momentum experiments. You're making free momentum, which is free weight. So somehow you're creating weight without, any way to do that. It's free energy nonsense. Momentum is real. It's a real physical phenomenon. And if you make free momentum, that's a real thing. That's real free energy. And all of these arguments lead to the creation of free momentum. All of their bad arguments.
About that. Well, I'm going to start you with what I think we're all pretty familiar with, is that...
So it starts with the canard, okay? It's not Newton's formula. It's not F equals ma. It's F equals mv. It's the change in your momentum. And that's all that ever matters, is the force will create momentum. Force is momentum. The force can be applied with an object moving with a momentum. I can have the force in a big object moving with an mv, and the force and its momentum are exactly the same thing. There's no difference between its force and its momentum. And if I roll it on a surface and all the momentum goes into the surface, the momentum will now be in the form of heat, but it's still going to be little things moving with velocities. And if I add up all the little things, mass, and I add up all their velocity, it's going to equal the same as the mv I started with, because I can't make or destroy momentum. I have to just exchange it, always.
Mass has inertia.
So mass doesn't have anything except mass. And it just says, you want to move me, apply a force and I will move. A significant force, enough force. If all the atoms can't move, the object ain't moving.
Anything with mass has inertia. I think we
So it doesn't have anything called inertia.
understand that. And what is mass? Mass was told to me in high school, mass is just a measure of the amount of stuff that you have.
Yes, and so you can think of it as in Planck units even. You can think of the force as in Planck units of little discrete bits, and you can think of the thing you're hitting as discrete bits, and understand that that's all they were talking about. If I have a 1 bit that has velocity and I stick 10 more bits on it, well then I'm going to reduce its velocity by a factor of 10.
If you have more mass, you have more weight. And if you have more mass, you have more...
So again, weight is just measured in gravity, blah, blah, blah. So nothing has weight. It has momentum. So the simple argument is that everything is momentum. So if I weigh something, the scale moves, okay? It registers a weight. The fact is I can do the same thing going this way. I can give the object a velocity into the scale and have an impulse measurement. And that impulse measurement is the same exact measurement as this. It's not any different, except this is gravity is constantly pushing, so it's a constant. It'll keep registering on the scale. But it's the same thing as this, and I just lock it in that position. Okay, it's the same thing, same exact pressure. It moved the scale, it pushed it a certain distance, that's the compression, and I just aren't constantly doing it. I'm not creating it constantly so the scale can spring back. But unless I lock it, of course. So there's no, it's not magic. And this I would argue is 1 mile an hour. So if I take an elephant, move it 1 mile an hour, it'll read elephant. If I take a mouse and move it 1 mile an hour, it'll read mouse. Okay, it'll be exactly the same measurement that you get here, because weight is just momentum. You're just measuring something's momentum. And momentum created by a constant pushing, or momentum created by an impulse push. But there's no inertia.
So whenever I need more space in my wardrobe,
Oh,
I
that's unfortunate.
sell everything I don't wear anymore on Vinted. Download Vinted.
Start the season with up to 60% off trees, plus save on floral, decor,
No,
and
I
more.
don't think I
Only
will.
at Michael's.
No, I'm not going to do
Resistance
that.
to acceleration. Newton's second law here, that we learned very, very early on in high school physics.
So that's unfortunate, because, I guess I was lucky, because that's not how I learned physics. Okay.
describes the ratio between how much force we apply to an object and how much acceleration we...
So velocity that is acquired, and that's all it is. Acceleration is just acquiring velocity. So acceleration is changing velocity. It's not some other thing. It's not a magical thing. It's just a change in your velocity. So again, just kind of bullshit.
Get as a result. And this equation tells us that the more mass you have, the less acceleration you get out of a given force.
Right. So the more things you have to push, the thinner the pushing power goes per thing. So it's just the peanut butter on a piece of bread thing. The bigger the piece of bread, the thinner the peanut butter. Duh. Okay. What does that have to do with inertia?
So from this equation, we can describe what's happening here is there's some resistance to acceleration. And we call...
All right, so there's no resistance. There's just this simple obligation to make the transfer. You have to have good contact to make the transfer, and that's all there is making contact.
An inertia. If you apply a force to something, it will accelerate, but it's the amount of acceleration you get
is completely proportional to the amount of mass you're pushing. So the 10 marbles is harder to push than 1 marble by a factor of 10. So again, there's no indication that anything applies a resistance unless you're putting it on a floor or a table and gravity is applying a pressure, pushing it into the surface, creating more friction. So obviously, again, the faster it moves, the less friction per inch. Absolute fact.
It's resisted by how much mass you have. And so that's how this was described to me, and I think most of us think of things in these terms.
So I don't.
But putting this together, we look at this equation, and we're going to run with this. What we're literally saying here is this m term is the amount of resistance to acceleration that you get.
All right, so this is not very interesting, so I don't know how far to go with this. Yeah.
And that was literally the definition of the word inertia. So
again, it just has to do with this idea that somehow things resist being moved when no, you have to give them energy to move them. It's just not that complicated. They're not resisting motion. They're just saying you have to push me for me to be pushed. You have to force me to move. I can't move without being forced.
maybe, rather than saying mass is the amount of stuff in an object, which was sort of vague and unhelpful,
I think it's perfectly reasonable.
maybe we could say that literally mass is inertia.
There you go. So why'd you even have this whole conversation? Why didn't you just say we have a silly word for a concept that doesn't really exist and all there really is mass? And frankly, all there is velocity. There is no such thing as an acceleration. Acceleration is just a change in velocity. Velocity is the core thing, and there really isn't anything called an acceleration.
Mass is the resistance to acceleration.
All right, so again, there's no resistance, and there's certainly no resistance where lighter things are harder to push. Okay, that somehow all of the facts of momentum break down. So if I have 5 marbles and I have 10 marbles, there's no principle that says, oh, when I push the 5 marbles with exactly the same force, they'll only go 1.4 times faster. So even though there's half as many of them, I won't get twice the velocity. I'll only get 1.4 velocity, because somehow if I do get twice the velocity, that would be free kinetic energy, and you can't make free kinetic energy. So again, the whole thing is just so sloppy and stupid, and I really shouldn't have to make these videos. It's just such a bad theory. Play a little bit more.
More mass, more resistance to acceleration, less mass, less resistance to acceleration.
Completely proportional resistance, if there's any resistance, and there is no resistance, especially like I said in space. Obviously on frictional surfaces there's a lot of resistance to motion because the thing is making contact with a surface, and you have to push the energy in and push it into the ground at the same time because it's leaking energy, because it's touching something. But if I free fall it, if I just drop it, then there's no such resistance. Twice the force is twice the velocity, as Newton said. 3 times the force, 3 times the velocity, as Newton said, not as this nonsense says.
And that's what inertia literally is. What I'd like to do now is delve deeper into what actually causes this phenomena of inertia.
So we know there's no phenomena. So he's saying what causes this phenomena? He just says it's the same thing as mass. And now he says what causes this phenomena of mass? I mean, it's just too ridiculous a statement.
Newton's law here describes how it comes about, how it works.
So it's not Newton's law, it's just wrong, it's just a lie. I don't know why all you people feel so comfortable in lying about what Newton said. Newton said twice the force, twice the velocity, 3 times the force, 3 times the velocity. He didn't say anything about per second, and he certainly didn't say 32 feet per second squared. He didn't say 32 feet per second squared. He said 32 feet per 1 second. 1 second, you get 32 feet. If it's 2 seconds, well, then you get 64 feet per second. You know, and if it's a half second, then you get 4.9. That's what Newton said. Not 4.9 meters. You know, I'm using feet because Newton used feet, but whatever.
You know, how much we're going to get, but it doesn't really tell us why. Can we go deeper and ask why?
All right, so this whole can you go deeper, can you drop 4 pounds 1 foot and 1 pound 4 feet and prove that two things with different momentums, completely different, I mean, you know, twice as much momentum. One of the objects has twice as much momentum, and somehow they're going to create the same impact force. So something with completely different momentums create the same impact force. That's your theory. You never tested it, and it's garbage.
Background. Newton thought that inertia was an intrinsic property of mass. All mass has inertia in this ratio to...
Look, I mean, the fact that Newton implied that there was some resistance to motion, that's his business, but I'm just saying there really isn't any resistance. Nothing is resisting being moved. There's just circumstances in which, well, yes, if you have it cemented to the floor, yeah, then you have to move the whole floor.
The point where you can just put mass into the F equals ma equation. That is what inertia is.
It's just terrible. So it should, again, Newton's formula was force equals the change in your momentum. That force equals momentum. Force is just another form of momentum, and that's all it is. That's all it ever will be. That's how the universe does, in fact, work.
But Mach had a different idea. Mach definitely thought that all...
Yeah, well, Mach, I don't know why he's bringing him up, because he's just loop-de-doo.
Motion must be relative to something, as we've discussed in our relativity investigations. So if all motion is relative, does that not include acceleration?
So again, it's whatever the hell this relativity crap is, it's just obviously, I would argue that it's only incidentally relative. But there is absolute force, and there are things that are actually carrying force and things that are actually carrying less force. And you're just seeing the difference between them. And we can't tell often what object has the absolute more force. But the fact that we can't tell doesn't mean it isn't happening.
If acceleration is relative, then this concept of inertia, which is resistance to acceleration, must also be in the same way relative.
All right, so there really isn't any relativity. You either are increasing something's velocity or you're not. And obviously when you're increasing its velocity, you could be technically decreasing its velocity from our relative perspective. But it really doesn't matter. The consistency of mv, the fact that you have to conserve it, always applies. So it doesn't matter who's doing the absorbing and who's doing it doesn't matter who has the $10. I bang into something. The fact is, all right, is that one of us has the motion that moved into each other. One of them has the $10, and you're just going to split it. And that is the truth. And Newton's bucket kind of proves the case in making the argument that there's no way circular motion always defeats any notion of relativity, because it always has to be added velocity. It's always added motion. You can't create any circumstance where you're taking energy away, because that would mean the whole universe has to be spinning. And obviously it would be three bears, Goldilocks silly, to sit there and start arguing that, oh yeah, we're just not aware that the whole universe is going to care that I spun a top on a table. And then now the whole universe is going to fool us by spinning in the opposite direction. And we're supposed to believe that that's happening. And now, of course, it's not happening. Alright, so it's probably enough of a video. I mean, this is quite abstract even. Yeah. So, we won't bother. And such, yeah, so that's enough. So I'll send emails to these fellas and see if I can get one of them to pay some attention to these arguments and respond in some way. Yeah. We'll see what happens. I mean, just to acknowledge that physics really hasn't done any of these experiments. I mean, Mythbusters had to crash cars, and they didn't find any kinetic energy, by the way. And, you know, they've never stuck thermometers inside of ballistic pendulums. I mean, nothing. They have done nothing to shore up the truth here. And it's just a lie to say that when I convert energy from a big mass to a small mass, or from a small mass to a big mass, that I can actually conserve both kinetic energy and momentum. Because I can't. It won't happen. Alright, so till the next time, and such and so forth and whatnot.